have to be expert in the different domains. You have to be the expert in the area of signal processing. You need to understand that what is the artificial intelligence, how to apply the artificial intelligence and the machine learning for the forecasting of the load and these all the things. So that's why we have organized and we have invited Dr. Sandeep to speak to you so that you can be more wiser with this all the talk so that you can think that how to implement that what you are doing here in the classrooms. You should think to apply in a more collaborative way by the application of different domain knowledge. So again, I'm thanking to Professor Sandeep for accepting our invitation and sparing time to be with us. Thank you again, Professor Sandeep.
Thank you, sir, for that beautiful welcome speech. I now take the honor of introducing our first keynote speaker for today's session, Dr. Sandeep Kumar. He is an associate professor at IIT Delhi and leads the MISN lab, advancing graph machine learning, AI, and intelligent systems across healthcare, neuroscience, security, and finance. As lead of Adivani, he develops AI platforms for tribal languages, promoting digital inclusion, cultural preservation, and equitable societal impact through teaching and research. I would now like to request Dr. Sandeep to deliver the keynote address on Towards Trustworthy and Scalable Graph Machine Learning, Challenges and Emerging Solutions. Please, sir.
Hi all. Very good morning. So before we'll talk, let's start our talk, right? Just very establishing very simple connection. Okay, your teacher, current teacher was also my old teacher. So Professor SK Sinha is also my teacher when I was doing my BTech in College of Engineering, Roorkee. So I did my BTech from 2007 to 11 in Electronics and Communication Engineering department, and then Masters and PhD from IIT Kanpur. And there my domain was signal processing and optimization. Right? And currently now I'm a faculty at Department of Electrical Engineering and ERD School of AI. So you can see there was a change of area continuously, right? And now we are at the time of artificial intelligence, AI, and AI is kind of over encompassing that everything around us will be affected and is already being affected by AI. But one good thing with AI and one good thing with all of your department is it seems that AI is an area of computer science, but slowly or very strongly it is believed that it has also been established that it is more of a domain for core engineering. Because see, at one point of a time, AI will become commodity, right? It's a tool. Am I audible till last bench? Or should we turn off the fans? आवाज आ रही है? Fine. So primarily moving from the tool, which is AI, right? It has to be applied to domains. So AI in isolation will become a commodity, will become a tool. And when it will be applied to certain domain, it will add value to it, right? So in order to have its utility, strong domain knowledge is very important. So after 5 years, everyone will be ML engineer, AI engineer, but very few would be domain experts. Right? So electrical engineering department, core engineering department will have to reshape its whole orientation. So at IIT Delhi, we are doing a curriculum revision, primarily to like utilize this aspect that we cannot be in isolation only doing the code stuff. We can also not be saying, you know, those areas are not for us. Right? So have to have a balance. We need also to evolve in a manner where we also understand that part of the word. That part of the word means AI as a tool or AI as a solution. Right? So this conference, attending this conference will help you directly or indirectly to achieve that goal. So the vision of my talk, I will be very brief. My core expertise is on graph machine learning. I will talk about it. How much time we have for the talk? 40 minutes, right? I need to connect my laptop. Correct.
निकाल दे ये मैं ऊपर
Shall we start? Start करें? Fine. So as the title suggests, right, we would be talking about trustworthy and scalable graph machine learning. So specifically to graph machine learning, we will be talking in detail, but trustworthiness and scalability are one of the two core issues of current AI ML deployment. Right? For any system to be completely useful, right, you need to have a trust with that system. And trust comes after many factors, right? Whether they are robust or not, the tool which we have designed, right, are they able to do the task beyond their utility? And can they be reliable against adversaries? These are few of the core issues which are still we are facing, but we will be more talking this in respect to graph machine learning. So let's see what is graph machine learning or what is graph data. You, I think most of you are undergraduate students, right? So the slides I have prepared would be slightly advanced, but I will try to cover the core crux of it, right?
ये सर स्लाइड्स जानी नहीं है सिर्फ देखना है इसमें शेयर
अब चेंज हो रही है स्लाइड हाँ ठीक है So wherever there are mathematical details, you can try to skip mentally. And if you are able to follow the big picture, it would be fine. But if you have any doubt, please feel free to ask your doubts in between. Okay? The idea is not to exactly explain everything. It's just to get motivated and understand the area in a big picture. Right? So when we talk of a graph data would be something that there are set of points. Each feature you can understand, right? And apart from the feature itself, you also know how these features are related to each other. For example, your friendship network data. For example, the recommendation engine, how you are recommended a particular movie. These all are based on graph data. There are plenty of examples of graph data. For example, your road network data is also a graph data. Use it daily. The Google Maps are based on all the Google Map engine is based on utilizing this data structure where road junctions are nodes, roads are edges, right? Traffic volume at each node and roads are the features of that graph data. Your social network data, right? Social network could be of anything, maybe of a particular hobby group, political group, right? Or particular work group where nodes are individuals and connections between those individuals are based on certain similarity relationships. Your brain network, brain data is also a graph data. So what is brain data? You have a brain. I think we all have a brain, right? And we capture signals. And there are different types of signals we capture. fMRI we capture, EEG signal we capture. And how our brain functions can be determined by how each of these regions are interconnected or how each of these regions are playing together. If you have certain issues like dementia or depression, the connectivity pattern will vary, right? So brain data can also be represented, not can, is also represented as a graph data. So parts of a brain are also known as the regions. They are nodes, and how they are related at particular time are the edges. So it's a graph data. This is a molecule, right? A chemical molecule. So chemical molecule or any molecule is also a graph data. So you might be hearing a lot about drug discovery, right? You also have heard about the protein folding for which recently chemistry Nobel Prize was awarded. Right? They all are part of graph data. So how you represent it? So there's a molecule. So each of the atoms are represented as node. Their chemical affinity as a H, right? And depending on what kind of chemical behavior those two elements would have, depending on that. Your circuit is also a graph data. So this is one kind of a circuit, right? And to break it down, so different junctions, different parts of it are nodes, and how they are connected is represented as a graph. Your weather pattern data or heat pattern data is also a graph data. So in a nutshell, graph data is universal, right? And it's a very powerful representation. So in terms of the evolution of machine learning, you might have heard that 10 years back or 5 years back, most of the applications which were coming were primarily from the vision of image data, right? The moment graph data came into the picture and people started utilizing the graph data, we suddenly like entered into the realm where we can almost model every problem. Every problem means molecular problems, simulation problems, all. So there is like mathematically, there is also a jump. The regular image data sits on Euclidean space. And the moment we are able to represent something as a graph data, we move into a manifold space. So in terms of dimension, you can see it's a low dimensional space, but very rich. So I just have put some of the snapshots of recent publications on graph data from Nature. Nature is one of the best venue for the publishing, which have a direct impact. So these all are some publications related to graph data, not mine, but in general covering the area. And you can see almost every area from how to design an best operative procedure to how to design RNA sequencing to designing like predict phenome properties. So from chemistry to physics to logistics to almost everything you can see are, and these all are very recent papers, right? So graph world is very important, very powerful. And there was recent also a kind of an article again on Nature that how representing something as a graph data will overall change the dynamics of possibilities, right? So they have written an entire article on the utility of graph data. Okay. Why graph data is actually important, right? So in a simple sense, you can see data has shapes. Okay. So these all are different shapes of the data. And a non-graphical representation somehow will make the whole world flat world, right? And if you want to capture the shape of the data, you have to move beyond the flat world, where graph-based representation come into the picture. Just a And those who are coming from the pure sciences or physics kind of a background, you might be knowing about the Laplace equation, heat equation, wave equation. The underlying principle of all these phenomena are tied to a particular matrix, which is known as a Laplace matrix. And Laplace matrix is nothing but the discretization of the graph data from continuous domain to discrete. Okay. Fast forward. One of the viewpoint of what do we mean by data has shapes and we want to capture that shape. So suppose your data is sitting on a manifold. So you can think of, you have a paper, right? Just visualize the paper, and when it's flat, then the data points are on a flat space. Distance, actual distance, what you think of equivalent distance makes sense. You make a fold of it, right? You make a fold, then even if geometrically these data points from this fold to this fold are nearer, but on that manifold they are far. So that can be only captured when you represent this as a graph data. So you learn the neighborhood, that neighborhood project, then you have a graph data, then you operate. So in the hindsight, you are able to capture the difficult geometry of the data, and thereby it becomes useful for you. Fast forward, why graph data? graph data, again, it's a very intuitive way to represent your data. In many cases, it acts as a final tool, or in many cases, it acts as an intermediary stage. So you have raw data, represent with graph data, use that graph data to build something further. The area is both challenging and satisfying in terms of it's highly fulfilling. Why it is challenging? Because in order to do well with the graphical models and graph data, you need to have a grounding in statistics, graph theory, optimization, and engineering, right? So understanding these requires all these things. So at the same time, if you have something represented as graph data, it will have a direct impact on all these fields simultaneously. So let me just, it's not new. Okay, graph-based ML or graph-based data analytics is not new. It's age old, but the shape of it, the way how we process it has evolved a lot, right? I'm just focusing on learning kind of a problem, but in core statistical mechanics, physics, interplanetary galaxy analysis, and all graph-based representation have been widely utilized and not new from thermodynamics, Boltzmann's to now we have been utilizing. But now we are primarily trying to show the relation from the part of learning side, right? So one of the learning side to see how graph data is utilized. These are the digits, right, that you wanted to predict. For some of the digits, you know the label, and for some of the digits, you don't know the label. The classical ML problem, right? And you want to predict whether which digit that data, which digit is that particular data. So ideally, if you will do independent of graph ML, you will be requiring a lot of label data, and label data is costly. Right? So what if you learn the graph representation of it? So now you have a graph. For some who know the labels, and the graph is meaningful such that those who are similar are connected, those who are not similar are disconnected or not connected, right? So you can use label propagation. So label propagation can be utilized. Why? Because you have a graph-based representation, and because you can use label propagation, so it is only true only when you have the true representation of the in form of a graph. Again, for from the teachers who learn the graph. So there are ways how to learn graph. Mathematical formulas. So there are smooth signal based modeling, and there are probabilistic graphical based models, and most popular is the k nearest neighbor graph. So you compute the equivalent distance, any distance, right? And if the distance, you threshold that distance, in a sense that if distance is less than 0.5, to say they are connected. If they are greater than 0.5, then they are not connected. So there are plenty of ways to convert raw data to a graph data. Yes. So in this case, from raw data, you converted to graph data, and on top of it, you have applied the stable property. So this was the method used in around 2003, 2004, before the advent of deep learning. Other line of thought, see, suppose you want to learn a classifier. You know what is classifier? So are you helping or disturbing? What is your job? To help facilitate the, so it seems you are disturbing by talking to almost everyone. So why you are responding? You have to ask something or ask me? Okay. So yeah, what we have here, suppose this was your data, right? This was your data. And you wanted what? You wanted to learn a classifier. What is classifier? Classifier kya? Any sense of ML technique? Any of you? No? So this would be one of my suggestions, that you make time to learn it. Otherwise, you will not be employable at any stage. You have to do it. You have to do it in terms of whether it's a part of your curriculum. And now the things have also evolved a lot, right? You have everything on your fingertip. You just need to make best use of it. So apart from the regular curriculum, you also have to continuously learn something on a regular basis. In those guys who are being laid off, those who are not able to relearn things. There is no dearth of job these days. There are plenty of jobs, but the skill sets have changed. The regular legacy software is no more, the understanding of a legacy software is no more sufficient. The understanding of 10-year-old techniques are no more sufficient to continue your job. So job is not limited. There are plenty, but you have to have a habit of regular upskilling yourself. And these days, upskilling have become very simple. The same platform, the same YouTube, the same where you see the real content, right? There you have all the things available. You just have to dedicate almost 2 hours of your week to learn something extra. And if you will not inculcate this habit now, then future would be very terrible for all of you. There is the way things are changing. None of you will be able to survive in the race of maybe jobs or doing something better, because everything is being automated, right? And if you will stay mediocre, then of course you will be replaced. And in order to be useful, you have to regularly update yourself. So just make best time of it. Sorry, sir. So you have mathematical cost at different layers, right? So suppose if there is a mathematical cost on pre-processing of the data, primarily for with the graph-based models, pre-processing is quite an issue, because the moment you have represented raw data to the graph data, earlier data was n-dimensional space, so complexity was n. We represented as a graph, so you have introduced extra edges. So complexity has increased to n cube. So pre-processing is many times challenging, but after that things become much better. Okay. Yeah, so this was whole phenomenon 2024. In this case, what I was talking about is, suppose I only have two label data, right? What do we mean by two label data in terms of what is deep learning or machine learning? Just saying that I give X and Y, pairs of X and Y. There is some kind of a mapping between X and Y. With the examples of label data, I want to learn that mapping. So when you only have two label data, the kind of a classifier that would have learned would be the straight line. That would not work better for you. But in order to do well, what you need to capture the geometry of the data. And you can only capture the geometry of the data by putting it as a kind of a graph. So let me just talk. So by now we have kind of made ourselves comfortable with the idea that graph is a important thing. Graph-based data is going to help us, right? And if there is a possibility to represent something, and if you are allowed to represent something as a graph data, you should be using graph-based representation. Okay. And that is my current research area. And also this is a very active research area. And I have given the evidence by quoting different Nature publications. My group primarily focuses on these two aspects at IT Delhi. On the graph dimensionality reduction, geometric deep learning, private and federated graph machine learning. So these are from the algorithmic side. Algorithmic side means we develop tools, methods, mathematical algorithms, which can be utilized to any domain. The other side is I work with the domain experts. So we have very active projects with AIMS, with Penn State, the medical college or university. I don't exactly forget the name. Gravity, like the gravimetric data analysis for rainfall prediction and analog circuit design. So what we do? This one. Yeah. So how it is applicable? How it is applicable? I will show you. So we had a very nice paper last year where we developed the first pipeline for using graph-based ML for analog circuit design simulations, and which was accepted to the best AI conference. So NeurIPS is one of the best AI conference. That was Yeah, because it requires domain expertise, right? Only knowing AI/ML is not sufficient. For all these things, you know domain expertise, and there where you guys have advantage. So you might have also heard a recent suggestion by Elon Musk and Jensen Huang. Huh? Physics and maths, right? If you want to learn something new, you learn physics and math because the new world will be very different. In every 1 year, we are leaping 10 decades ahead, like what we used to have a scientific advancement earlier. So, yes. So that is their biggest mistake. Okay. Okay. So these are all we focus on, and also a kind of a bit of advertisement. So we have a very big active group with many of the projects, and we regularly hire master students, interns, with strong math background and programming background. If you are planning to apply for internships and really serious about doing good work, feel free to write a mail to me. So my group name is Mission Lab, Machine Intelligence, Signals and Networks Lab. We currently have 19 PhD students and roughly around a team of 60, 70 folks are there, and very active UG participation is there. Okay. You wanted to take photos, fine. Okay. Okay. So see, currently what we will be primarily focusing on, there are three big issues. There are many big issues with the current AI system and people are solving it. One of the issue is that scalability. If I want to solve a problem, suppose Netflix wants to solve the problem of movie recommendation for billion scale, right? It's a massive problem, right? If I want to put the cancer study, the images are histopathological images, their processing is very challenging. So the size of the data is one of the big challenge, and it amplifies for the graph data because not only now we are processing raw data, we also have the graph with it. So if raw data was having n dimension, the graph representation will have NQ dimension. So we have increased the complexity. There is AI bias. How many of you know about AI bias? Anyone? नहीं? Common sense में कुछ नहीं आ रहा है. इतना तो AI use कर रहे हो. Bias to any example from your experience? You must have started using AI. Something related to AI. ChatGPT तो use कर ही रहे होगे. It's not biased. DeepSeek is biased to China. Yeah, so see, the bias also has many layers, right? They are trained, they're conditioned to be more favorable to a particular country by design. So there, by design, they have, don't talk, either. I will help you. So those are, of course, biased, but the way that problem is that they have intentionally trained in a particular manner that they talk good about China, right? That is a forced bias. But in general, unknowingly also, there is bias in AI. So for example, see, if a two-person, one male, one female, with same demography, same education background, same pay scale, same PIN code, apply for loan or apply for credit card, it is more likely that a woman's application will be rejected. More likely, not saying always. It is more likely by AI system, not by general system. Why so? So this is biased for the same thing, right? Except if so, suppose you have a data, right? D-dimensional data. All the attributes are same. Only one attribute is changing. One is male and another is female. System is biased against female, means they will reject the female's application. Why so? The AI model has been trained, but it has not been trained to be biased. But somehow, from the historical examples, they have mimicked that thing. Why? Because historically, women have less examples of holding credit cards. So favoring examples for women are less. So the model is biased against women. For the same crime, it has also been studied in USA. For the same crime, same thing, blacks are more may have more chances to be punished for same crime. So this is known as bias in the AI system, right? We intentionally do not do, but how the data set had been curated, how the data set was there historically, because of that, there is a bias in the system. So AI bias is a big issue. Okay. Noise in the data is a big issue. And there is also fairness and bias, something they are related. Okay. So this is a quite nice quote, right? By James Mickinson. The internet is a cauldron of evil. We all know on the internet everything's happening. And if you fully, and ML is coming out to be very powerful. So internet is cauldron, it's evil, and ML is so powerful. And without understanding ML, how can you marry both the things? Right? So the outcome will of course be one of the greatest devil. So understanding how ML system works is very important. So explainability is also a big issue. We are not able to explain the outcome of AI ML systems. So now we will take a sprint. We'll move quite fast because next of the details are a bit of mathematical. So I will give you a big picture. So we have a, suppose this is a graph data. You understand what is graph data? Set of nodes, connections, features, right? And if I want to reduce the data, size of the data to make the processing quite faster. So there are two ways you can do that reduction. One way is what? To let the number of nodes be same, remove the connections, right? Suppose I have friends, so all connections are not important. I will keep only few. That is known as the sparsification. I sparsify the graph. Another is you have a massive graph. Instead of looking at all the nodes, can we collapse a set of nodes together such that these all are having similar information in some sense? Can I collapse it from there to this? Fine. So in this case, number of node has reduced. So the graph size will also reduce, right? So yeah, so this will help us in doing what? So whatever we wanted to do here, if this is equivalently capturing similar amount of information what we had here, then I can be using this. So this is what we will focus on. So in a nutshell, mathematically, the graph posting problem becomes what? If you have this graph, I want to learn this graph. So from there, I need to send some of the nodes together, collapse it, right? So essentially, I want to just learn this mapping matrix, right? So real world problem is now posed as a simple mathematical problem. It's not simple, it's a combinatorial problem. Solving it is not easy, but now you have a sense, right? Now you can actually do things. Maybe you can, so how we solve a problem? So you start with the real world setting, right? You pose this as you abstractify as much as possible and pose it as a mathematical problem. The moment you pose it as a mathematical problem, then it becomes solvable. Some mathematical problems cannot be solved exactly, but you approximate to solve it, right? But you can solve something. So there the engineering principles come into the picture, right? Otherwise, in air, we can be solving everything. But the fundamental rule is what? Can you put your goal in form of equations, right? And that is why all the advancements in engineering and all have developed, because now we know what to do here. So yes, learning a quotient graph, or a very simple example, this to this is nothing but learning this mapping. What is this mapping saying? This mapping is saying 1, 2, 3 is mapped to first supernode 1, 1, 1. To this, so this is 1 and this is 0. So mathematically, what is this? This is also an orthogonal matrix. Orthogonal matrix means if you will multiply this column with this column, inner product, it will be 0. So there are mathematical details. I will skip it. It simply says that if you know this C and there is a matrix of this as theta, so how this and this will be related? So this relation is this one. And the overall sense of this C matrix in form of abstract set notation. Okay, so let me give you one example here. So when we have graph data, right, you have connections and also features, right? So the one set of example of feature is this, and another set of example of this feature is this. Ideally, for a graph data, what do you prefer? This or this? Can you use common sense? What do you will prefer? This or this? First one? Why first one? blue is one type of a signal and red is one type of a signal. Suppose Netflix wants to build a recommendation engine and they want to learn the networks, right? Where each of the node is one person. If so, this means that if V6 is watching a movie, something similar set of movies are being watched by V7, right? That is why the similarity of signals means. In this case, someone is favoring a horror movie, someone is favoring romantic movie. So I cannot be using his new watches to recommend movies to him, right? So these kind of graphs are known as homophilic graphs. But how you quantify it? So there is something called Dirichlet energy. Dirichlet energy simply tells what? To take the difference, square it, whatever weight is there, you multiply with it and sum it over. Okay. See, whatever we are representing here is what is a toy example. But when we implement something, we do it at scale, millions and billions scale. We cannot see it. You have to come with a one kind of a statement or mathematical operations which will do the job for you. So this number will do the job of the visualization that you are doing. Okay, now when you compute this number, the number is what? Fi is this value, Fj is this value, Fi minus Fj square multiply with Wij. So pairwise difference square weighted by the weight summed over all possible connections. Sum it up and sum it up. So if this value is low, it means what? There is less of disagreement. If this value is high, this means that there is more of a disagreement. What you want to prefer? Weights are given. The weights are given. Graph weight is given to you. In this case, the graph is given to you. Now you want to operate further on it. So that's where I started earlier, right? So our audit, you learn the graph weight and then you do this all. So either graph weight could be given to you or you learn the graph. In this case, weights are given to you. So this gives you a number, right, to be utilized for making, indicating that if the value is less, this is the kind of a graph that would come. If the value is high, this is the kind of a graph that would come. Moving further, the problem statement for doing a meaningful graph portioning will become, just to give you some sense what it does it mean. It is a graph matrix. Graph matrix is theta. That is theta. I want to learn C. So this is an optimization problem. Means what? Given theta, I want to learn this theta. Theta is the representation of this matrix, right? And the features on top of it. So given feature is X, the quotient feature is Xc. And this is the energy that I was talking about. This is the energy. F transpose LF is there. So that is X transpose theta X. So just to understand, make you understand, this particular term, this term and this term is just forcing from here. If there is an N node, I will be mapped to a K node. And this will force on top of it. The graph will be smooth in nature. Okay. Don't bother about the mathematical digits. Just get yourself comfortable that whatever we discussed so far is now being represented as a mathematical equations, which can be solved. And when you can solve it, you will get the desired solution. When you have the background, you will be able to understand. If you don't have the background now, you may not understand now, but in future you may. Okay. And there are steps how to solve this problem and this. Okay. So let's move fast forward graph portioning where we have utilized, right? Let's see the big picture application. Massive data to smaller data, how you can use? I want to train graph neural network on this. Okay. Instead of this, I train on this. So I scaled up I made the overall computation much faster. Using the same thing for histopathological image analysis. So I have to conclude. So I will primarily focus on some applications, right? Where we utilize next? We utilize also to do the epidemiological study. So during the COVID, you might have heard this topic, right? What is the infection rate, right? If someone has come into the radius of something, right? Whether that person will be infected or not infected. So that comes under the study of epidemiological parameter estimation. So in general, the contact network in this case is quite big. Doing a simulation on that is difficult. So we perform the simulation and study on the smaller graph and check the accuracy on the larger graph. So there also we handle the issue of scaling up. So how much time we have? 5 minutes, 2 minutes, 5 minutes. Okay. Okay. Next, very quick, that's the base kind of a thing. See, we have data, right? On that data, there are sometimes adversaries and sometimes noises, right? So any ML model, if suppose this is visible to you, I add some bit of noise. Visually, this is what you will get, right? To us, there is not much of a difference. Still, we can understand that, but ML model will not be able to process this image because it's so much, any minute amount of perturbation affects a lot for the analysis. Now, look at this image. If you are designing a self-driving autonomous vehicle, and if you are riding behind this car, what you will do? You will be stopped forever because your system will sense what? There is a cycle crossing the road. It's not, they will not sense what? The cycle has been put on a car, so I can have the same speed as a regular car. So in this case, there is no adversary, but nature plays the gimmick, right? So your models should be robust against these things. So one of the next active frontier in general is also the robust machine learning, and my team is also focusing heavily on robust machine learning. So one of the big picture example is, suppose this is the image 7, right? And there is adversary. The adversary, it has been, instead of looking like this, it is looking like this, looking like this, looking like this. If adversary is bounded, it will be around this circle. So if your model has to be robust mathematically, what does it mean? ML does what? Learn the embedding for it. So suppose it learn the embedding in the higher dimension. So if you force the embedding to be also lying in particular radius, then that becomes robust. So that we followed with the ellipsis part. So let me wrap it up. Sorry for this delay. I will just give you some applications, more picture, better applications. This one, an analog circuit. Yeah, so this is the example. Okay. So this appeared in NeurIPS. So what we did, so when you have, there is a cycle of analog circuit industry or any circuit industry, right? First, you do a lot of simulation. Suppose you are designing a particular circuit, right? You have to do a lot of simulations to come up with a stable configuration. And those simulations are quite expensive. Okay. Cadence as a company is entirely devoted to these tasks, where you do simulations, validate, and come up with the right set of configuration. Okay. But coming up with simulation is very expensive. So can you learn a model, right, which can do the simulation for you? Simulation means my goal is that this circuit should have this figure of merit, should have this length, should have this noise ratio. These are all things I wanted to have. But see, as I will increase the number of requirement, the parameter space will like exponentially increase, maybe go to millions and billions. That is not possible. So there what we did, we started with some simulated examples, learned the graph of it, and then formulated the issue of simulation. So graph ML helped here. So I hope this is ma'am, this image is somehow clear to you in terms of, this is very simple. What we did in Spice simulator, right? So you start with Spice simulator, do some simulation, and for rest you do not do any simulation. You mix those things, learn a graph, and then do level propagation. This is the big, that is the big picture that we have done here. We applied the graph ML to brain study, and we did the depression analysis, different spectrums of depression. So there are 3 different spectrums of depression, where there is a recurrent depression, there is a non-recurrent, right? So in terms of the goal is what? You take a person, take the fMRI signal, just based on the fMRI signal, detect whether the person is suffering from depression or not. That is the goal here. And we did it. One of the nice study, what we actually got, women are more prone to depression. And this was also very evident mathematically from our model, and clinically also it was validated. So one of the latest outcome of our lab, very recently, You may find it very interesting, right? So tribal language. So for India has a very rich linguistic diversity. More than 15,000 languages are there. And for tribal languages, there are no AI models, no any model, right? So because of that, what is happening? Around 10 crore population is not utilizing the full benefit of digital revolution, because most of the things are either in Hindi or in English, right? And to some extent, to some scheduled state languages, but nothing in the tribal. So this multi-institute project that I led, where we were the first one to develop a AI translator tool for tribal languages. This was launched on 1st of September by Minister of Tribal Affairs. And it was also appreciated by our Honorable President, like Draupadi Murmu ji, right? That this would be a historical milestone for this thing. The app is available here. If you want to use this app, please feel free to download it, use it. And it is also available in form of a web portal, that is adivani.tribal.gov.in. We have a very active team here, and we are those who are interested in language technologies, right? And to create impact at a massive level. We are also opening a company on top of it, where we would be opening to hire a lot of students, primarily to build new technologies or to move to new languages. So feel free to write to me about it, right? And use the app, provide feedback. Currently, the beta version is being launched. When everything will be tested and the ground report will be consolidated, then soon we will be launching the final version, and that may be launched by the highest office of our country, maybe by our Prime Minister or maybe President herself. Right? So this is so also one summary is that so AI is getting very powerful, right? I am not a linguist person, right? I am also not a core NLP person. But because I have some understanding of AI, I have some understanding of how things work together, I was able to manage a team who can work for it, right? So AI has that kind of a transformative power. And I am from your domain. My core training as a bachelor was electronics and communication. Right? So if I can do something like this, you all can do something. But the thing is, you have to, at each stage, you really have to look for what you are doing next. If you will follow the heart, you will never be able to find the right direction. So you will always have to question what you did previously and what you are going to do next. Oh, this is some subset of my team member. And yeah, so that's all. Thank you. Thank you for your time. Should I stop sharing?
Moving ahead, it is my privilege. Moving ahead, it is my privilege to introduce our second keynote speaker, Dr. Rupam Singh. She is an assistant professor at SDU Robotics, University of Southern Denmark. Her research focuses on robotics, automation, and intelligent control systems, contributing to cutting-edge advancements in robotic technologies. I now request Dr. Rupam to share her valuable expertise on beyond classical control towards cognitive robotics.
Hello. Hello. Can you hear me? Hello.
Yes, you're audible.
Yes, ma'am, you're audible.
Okay. Okay. Thank you for inviting me. I'll quickly share my screen. Okay. Okay, so you already introduced me, but then I would quickly like to give a brief about me. So here I'm an assistant professor in ST Robotics, and I'm very pleased to give an invited talk in the 6th International Conference on recent development in control and automation and power engineering. So, of course, before going to the next before going to the actual AI application in robotics, I would like to talk where I work, why my workplace. So I'm working in Southern Denmark University, and here there are like we have 6 different campuses: SDU Odense, SDU Sonneborg, Slagelse, in Copenhagen as well, and then Esbjerg and Kolding. So, but then the SDU Odense campus is the main campus of the Southern Denmark University. And inside this SDU Odense, we have again multiple faculties and then multiple department here. So we have business, we have health science, humanities, faculty of science, and then the faculty of engineering. So, but faculty of the engineering is we say so-called technical institute for engineering, let's say. And then inside of it also we have a multiple institute. So we have a mechanical and electrical engineering, we have a technology and innovation, Metz Clausen, and then McMcKinney Moller Institute. So that thing is specified that I belong to the McMcKinney Moller Institute. And then here in the McMcKinney Moore Institute, this is we call the so-called the cheese building because how it infrastructured. So we have multiple groups inside of it. We have a US Center, we have a software engineering, we have a biorobotics, we have applied AI and data science, and then health informatics and technology, and then also the ST robotics. So inside of the ST robotics, there's mainly 3 things that we focused. We focused on the modeling and control of a robotic system. We focus on the computer vision for robots, and then we also provide the simulation framework to the industries, because we have a lot of collaboration with the big industries. I'm sure you guys know about the UI Robotics, Mia, Franca, all these robotic platforms. We have actual in the engineering bachelor engineering students. We actually perform the experiments and lab simulations with these robots. And before going to the actual AI application in robotics, I would like to first briefly talk about what are the different robotic systems. So we have the service robots, we have the field robots. Service robots are someone that helps the humans into their daily life. We have a humanoid, we have a domestic. One good example for the domestic robots could be, I think everyone in these days have in their house this mobile vacuum cleaner. So it's nothing but then a robot, right? That's cleaning itself, right? So this is one thing. You can see that there are so many robots that helps in the medical. So they help with the elderly people in the hospitals. So these are like a different service robots we have. And then the field robotics, we have aerial, application, we have marine application, we have a ground application. So when it comes to the aerial applications, the drones are these days, everyone knows. And then in the drones, one very nice example I can give, the swarming of the drones. So you see, like now, in order to save the environment, we are avoiding doing this firecrackers, and we do this drone shows. So this is like one of the good example. And then of course, other than that, it's like for fun. But then for the surveillances in military, we use drones a lot. And then marine, we have a surface vehicle, we have an underwater vehicle. We have this self-driving car that could be like one good example of the mobile robots on the ground, right? And then what are the main research that's in current days is going on in these robotic systems? So if you see in the autonomy and the navigation, we have a trajectory planning and optimization. We have this SLAM algorithms that do the simultaneous localization and the mapping. We have this autonomous navigation and path planning. We do in terms of the sensing and perception, we have this computer vision and perceptions in the robotics. Yeah, we use the machine learning and AI for the robotics. So these are like one example. And then for the health monitoring, so let's say if some kind of a fault is occurring in your system, how can you detect it, isolate it, and then provide the reconfigurable control. So your system, even with in the existence of the fault, it can handle it. So that's another area of research that's going on. Other than that, we have human interaction and collaboration. So how can a human and the robot can work together? That is really challenging these days, because robot is nothing but just a machine, and it is sometimes becomes very hard to control, and especially when there's a human, then the safety comes really very important point. So that's like one thing. And then the robotic systems and coordination, swarming is one thing, like how you develop a network communication, or controlling through the different networks, and how they can talk to each other, how the one machine can talk to the another machine, or one robot can talk to the another robots, and then in coordination they perform some kind of a task. That's another area of research. And then here comes the advanced robot learning, which is all about machine learning and AI. So there's lots of deterministic approaches and methods that we tell a robot to behave or learn from the experiences. So that is also one kind of research area these days going on. Now, as this is all about the AI, so we should first understand what the AI is. AI is something intelligent, right? Like how we say, someone is intelligent, like based on how it's learning quickly, how it's learning or behave, and then when it learns quickly, how it takes the decision on the same experiences. So not only just learning, but then also taking a decision. So AI is all about mimicking the intelligence, and then adapting, and then taking a decision. So this is the main whole and soul of about the AI. But when we talk about the AI in the robotics, then there's multiple domains or multiple applications that you can see all around the world these days. And a couple of them I try to put in here. And you can see from the first is like a very challenging task is make your generally if you see a robotic arm, they have 2-finger 3-finger kind of grippers, and that's easy. It's just you have 2 fingers and you're trying to grab something. But then if you have a 5-finger, then you have almost 20 degree of freedom, and then you have 25 joints. Then it's really hard. And then if you are grabbing something really small, let's say if you're grabbing some a needle or a very thin object, then it's really hard that how much pressure you should put onto it, and in which angle you are holding it, what is the orientation of it, what is the precise, how can you get the precise force on it, contact forces. All these things are like very hard and complicated when you're doing these kind of manipulation. And then with the help of AI, what we can do, we can teach them. We perform something, we put the right amount with the help of the correct sensors and all, we can you can actually estimate the correct amount of force and you can grab it. So that's how the one application is that. And then high motor skills, let's say if the robots are playing some kind of game, table tennis or something, ice hockey or some any kind of where the any kind of example where there's motor coordination is required on a really high level, then again we can teach them through the AI. We have the imitation learning. In the imitation learning, we just teach robot to mimic what we are doing, and that's one thing. And then the reinforcement learning, on robot learning, physics inspired learning, how you can integrate the physics into the simple model of a robot or into a simple nonlinear system, let's say, and then how you can integrate it together and then make it feel more like a human behavior. So that is a couple of the examples in the robotics. But then for any of those things, for any kind of these application, first we need to understand what is the basic control structure for the AI in robotics or for to implement any of these applications. So first we should understand what is the modeling of these systems, and then what are the different control methods we are choosing. Are we choosing the optimization based method? Are we choosing the intelligent control approaches? So these are the different control schemes that available. But and as I said, like the modeling is the most important. So I have been working with this multiple different system. I have worked with the balancing robotics, we balancer systems. I have worked with the helicopter systems. I have worked with the drones and manipulators also. And then these days I'm working with this dexterous hand also. So first I'll try to give a rough understanding of these two systems. So if we have a helicopter system, that you have a yaw rotor and then the pitch rotor, and then you have to find the balance between these two and correct amount of thrust, and then how to make the attitude stable in order to fly it. And then balancing system is something similar. You have a two-axis control, and then you have to you have some kind of a camera on top of it, and then you try to balance the ball on the plate without falling it off, even though it's moving. So these are like a general, let's say, two robotic systems. And then I have been working for so long with these different algorithms, which is based on the probabilistic control, intelligent control, meta-heuristic methods. So these are different control schemes that I have implemented on the helicopter system as well as the robotic balancer as well. So if I talk about the meta-heuristic approach that I have been working with, the ACO, which is an ant colony optimization. But what is meta-heuristic? It's basically learning from the nature of the animals. So you have a large amount of population of these animals, and then you then one animal, let's say, start to follow something or start to do something, and then the rest of the population will follow it. So there's two important things in this: the operators and then the control parameters. The operators are the one; those are the leading, and then what are the let's say if we have let's say in this ACO example. So what the ACO example works, there's an ant, let's start searching for the food, and then it's going from one place to the another place. And then when it goes from one place to another place, then it leaves a pheromone. Pheromone is some kind of a liquid that is like a tracking thing. So when the second ant come and then it follows the same. So this is, let's say, one way of finding the path. But it is not necessary that all the ants will following, because sometimes there's a chance this pheromone might evaporate. When it evaporates, then they start looking for another solution. So and then in the end they try to optimize it, which one is the best, which one is the shortest. So there's like multiple paths, and then in the end they will find the optimized path. This is like how the ACO works. And then there's like a control parameters in these kind of algorithms could be like the population. So how in ACO, let's say the number of ants, how quickly the pheromone is evaporating, and how many iterations you are doing. So these are the basic understanding for the meta-heuristic control methods. And then how I did it, I used this ACO in order to tune the classical controller. So I have, let's say, PID controller, and how I am tuning my KP, my KI, my KD gain. And then initially it's like randomly, as I said, initially just randomly follow a path which has some kind of node, and then the nodes are like interconnected, and then they reach to the final goal. But then again, correspondingly, how you are changing the nodes, how you're changing the paths, the KP and KI and KD value will be updated. And then the next approach is the probabilistic control approach. So probabilistic control is nothing but then a control framework where uncertainties in the system, such as disturbances, noise parameters, are modeled as a random variable. So, and then when you model these as a random variable, you also consider the probability distributions of it. And then control design ensures that this performance and the stability should be a high probability. And what the assumptions is, like, let's say in general deterministic algorithm, what happens when you are giving some kind of input and then you get the same output. But then what the probabilistic control approach is saying, even though you are giving some kind of input with the involvement of the random numbers, you will get the every time the multiple or different outputs. So that is something is this delta, when you have this delta variable which has the nothing but the a huge number of random variables, and that will treat it as a noise in it, and then that's why you call it a M delta model. So even if you have a same kind of input, you are getting the different outputs, and then you assume that your system is probabilistically correct. So that's one of the method. This is a branch of the robust control, and then it's very useful when your system is unknown and or you have a non-linearity in the system. So I have implemented this probabilistic control on the my helicopter system, and I added the uncertainty or delta variable with the input in order to bring the uncertainty in the system, and then try to find the solution for it. So next is the intelligent control approach. So for the intelligent control, we should know that the normal model-based method is really good when you have no uncertainty, except if, let's say in the previous probabilistic control approach, we are adding some kind of uncertainty in the system, and then that's how we are finding the solution. But then the intelligent control is like, even though you don't have a model of the system, and then it's really good with the uncertainty handling, and then they are really good with the decision making, and then the online replanning, and then they provide the even in the presence of the fault, they provide the correct reconfigurable control. And you can find the application of this intelligent control approach in any area, and we talked about it earlier. So if I talk about the how I have implemented this intelligent control in my system. So I have used it with the UAVs or drones, as I said earlier. And then what it's doing, it's basically here we have a flight control block plus the reconfigurable block. So what it's doing, it's if there's some kind of a fault occurring, so uncertainties is added in the aerodynamic model, and then when there's this uncertainty, could be a wind or could be any kind of failure in the system, and then what it's doing, it's reading is the current state and then doing the state estimation, and then through the sensors it's providing to its model, and then model identify the what is the possible problems in the system, and then send it back to the and complete the close control loop. So this is the one of the intelligent control implementation. And then the learning approaches. So I've been working with machine learning, and then the subset of the machine learning, you can say a reinforcement learning, and then its application in the different domain. So if I talk about the machine learning, then there's three different major divisions of the machine learning: supervised learning, unsupervised learning, and then let's say this is the reinforcement learning. So when we talk about the supervised learning, we know that the what kind of data we have. So let's say if I'm talking about the data of a helicopter system, then we know that this is the yaw data that's coming from the yaw motors and yaw motor sensors, and then there's the pitch motor data that is coming the pitch motor sensors, and then we exactly know that if some kind of fault is happening, then this fault is coming from the failure of the yaw motor, or the like which component is failing, we know about it, and that is called the supervised learning. And then we mostly use this learning in the regression and classification. While the unsupervised learning is you have no idea what kind of data you have. You just put the random model, a statistical model on this, and then try to train it and learn it. So there's no exploration also in this supervised and unsupervised both kind of method, and we mainly use it for the clustering. And whereas the most interesting for me is the reinforcement learning. So where it's what it does, it is mainly the reward based. It learns from the experience and it interacts from the environment and get the feedback and then provide final output. So there's like you can call it is a trial and error method, but then again not just blindly trial and error, but then a valuable feedback with it. So and then this kind of methods are very adaptable to the changes. And then one of the example, the behavioral learning. So we are doing some kind of a sign or something, and then we want our robot to do the same thing, so we will do it and then it will follow it. But then also while it's following, it's learning like, okay, if it's following correctly or it's not following correctly. So so these are like main machine learning approaches. But then when, let's say, if I'm talking about something related to the fault classification and I'm trying to use the reinforcement learning or any supervised or unsupervised method for the fault classification or some kind, then what we need to do, then we need to first identify what is the kind of fault we are having, and then in which component this kind of fault is happening. So there's different kind of components that you can see here. It could be the encoders, it could be the sensors, it could be the navigation systems, and it could be like of course this corresponding to the type of motor you have. If it's a yaw motor or pitch motor, then it will be corresponding to that. And any kind of failure will eventually result in the failure of any task that you are performing. So it will fail to localize what are the changes that's happening. It will be not able to navigate properly. So these communication, if let's say the GPS is failing, then it will not do the communication properly. So these are the first we need to identify what are the components we have, and how we are actually gathering the data from these components. So if I talk about the sub items within these main items, would we like, if we have a driver unit, then in the driver unit we have a rotor, and not just the rotor, but then the controller of the rotor, right? And then what kind of faults we might see in the future, that the rotor faults, failure of rotor unit, or some kind of a circuit connector failures, but then it's coming all through or from the rotor unit. When it's the navigation system failure, then it might be possible some kind of transmitter is not working, some kind of a receiver is not working, some kind of a GPS system failure, and then still it will give you a fault. But then everything result in that your system is not working, but then you don't know which part of it's not working. So that's why it's necessary to diagnose it first, that which part is not actually working. So that comes under the condition monitoring and the safety of these components in the systems. So what I did was I tried to gather all the data from the different part of a system. So for the drone, let's say I have gathered the data coming from the actuators, coming from the planes, coming from the sensor units, and then we identify, because I am using, let's say, the supervised methods or supervised learning. Then it's more of what kind of fault is occurring we already know. So we already prepared the data, that what kind of the data we have, and then we do the data pre-processing. When we do the data pre-processing, we do use the discrete wavelet transform, like it's one type of transform method, but then there's like a menu. You can use the Fourier transform or short-term Fourier transform. There's multi, but then I use the discrete wavelet transform because with the DWT, you can analyze the signal in time domain and the frequency domain both. So that is the advantage of using the DWT. And then once you do it, then what it does, it classify all, it use the low pass filter and the high pass filter, and then give you the different kinds of features. When you extract these features, then you use this feature minimization methods. That could be like one method could be the principal component analysis method. And then once you have this feature extraction you have done, then you use the classifier developer. When classifier developer is nothing our machine learning model. So we can use the support vector machine learning classifier. We can use the multi-layer perceptron neural network. The SPDD, there's like thousands of the classifier, but then again you have to choose these classifier based on what kind of a data you have. So once you have these kind of data available, then it will go back to your it will classify that what kind of fault is happening. If it's a motor fault, sensor navigation system failure, all the some kind of sensor failure, so it will tell you that kind of fault and then classify it accordingly, because you have already extracted the features based on these from these data, and then it will develop a classifier overall. And once it does, then it will send back the signal to your controller, and then it will say, okay, this particular component is failed, and this data is responsible, or this unit is responsible for this failure, and then you provide the control for it. And then the controller, because we have this adaptive controller, so it will automatically reconfigure it and then send the signal, and then you will monitor your condition of your system. And then this is how overall you can do the condition monitoring and the safety for a system that's under the fault. So next is reinforcement learning. So I've talked about the supervised learning methods. Now I'm talking about this a little bit of the reinforcement learning. So in the reinforcement learning, we it's as I said earlier, it's a type of a machine learning where an agent learns to make a decision by interacting with an environment. So the main thing here, if you want to understand about the reinforcement learning, is these three and mainly 4 or 5 things: is the environment, reward, agent, actions, state, and policy. So when I talk about the agent, it's someone that takes the decision, and then the environment is something that how the agent is interacting with the environment, and then the state is something that what is the current situation of the environment. Action is something that what the agent is choosing, and then the reward is a feedback signal. So if I try to explain it with an example, let's say there's a robot which is inside of maze, and then the task is to find the path and then go to the exit. So what it's trying to do, it's interacting the environment. So the state is where it's its current position, it's where it's standing at this moment. Now it's like, let's say the 3 actions it has: go left, go right, and then go forward. So this has the actions as like these 3 things. Now the environment is this, of course, the maze, and then the reward is like, if you are moving forward, then you will get -1 point, but then if you're going left or right, then again you are getting -2 or -3, depend. It's up to you, completely up to you what kind of reward values you are giving. The moment you go out of it, then you'll get the 100 values of reward. So the thing is, again, sometimes you can also say, instead of giving the negative rewards, you can give the positive reward just for the movement, so that it feels like it's going in the right direction, but then it always can stuck somewhere. So it's better to give, like, take less steps. So negative means you should reach out of this or come out of this maze as soon as possible. So let's say if it's moving forward and then it's it finds some kind of obstacle, then it fails. So it will get now the thousands of the negative rewards. So this is something how it's interacting with the environment. So once we have this, and then robot knows like how the state how the actions is updating, how the agent is working with the actions, and then how your policy should define. So this is some kind of a workflow. And then there's different kinds of methods we have in RL. We have a model free methods, we have model based method, we have policy based, we have value based methods. So we have different kinds of methods also. And then there's different kinds of the RL algorithms is also there. We have a Q learning, we have a SARSA, we have this Q deep Q networks. But then the difference mainly between these Q learning, SARSA, and deep Q networks is based on what kind of environment is. So when you have a discrete actions, then you will be using the Q learning and then off policy. While its SARSA is also discrete actions, but then it's with on policy algorithm. And a deep Q network is discrete and off policy, but then when your system become more interactive, like for the maze example, there's nothing, you're just moving forward and doing left and right. But then if you have some different example, let's say if I have a robotic arm, it's and that is on the mobile robot, and that's mounted on the mobile robot. So then it's also moving left and right, but then also doing some kind of grabbing something, and then doing pick and place or some kind of task it's doing. Then there's more complex environment we have. And then that kind of situation we need a network, because a simple Q values is not going to help you. So and that's how these Q learning SARS and deep Q networks are different from each other. But then there's a problem with the deep Q network is that when you have the continuous states coming, not the discrete, then it will not be able to work properly. And then there comes the deterministic method, which is deep deterministic. One of the method is deep deterministic policy gradient method. So in the DQN, what happens? You have a critic network. You have this critic network takes all the states, and then you are giving the Q values in the end. While when you have a DDPG, then you have a critic network, and then you have a actor network. So what is happening here, the actor network, you see there's the states and giving the actions. So you keep giving the states and they keep giving the actions. So it is the agent is based on the state taking a decision. But then what critic is doing, critic is validating these actions, that these actions are working correctly or not working. So what critic is doing, it takes all the states and actions together and then give you a final Q values. Q values is the overall policy, let's say, a form of a policy set, like a multiple Q values you have, and then you know how your current state and then the actions we have. One more thing about this, let's say the on policy and the off policy algorithms is that when I'm talking about the off policy and I'm using the word the off policy, it means that you are in certain state, right? And then you are taking a decision based on what is could be your future state, but not your present state. That's your off policy, because it knows that, okay, what is the possible future rewards, and then for possible future action, and it's taking the decision based on that. But when you have on policy algorithm, it's taking a decision what is your current situation is. So if you are moving in the wrong direction, it will tell you at the right way, rather than you keep moving in that direction and then again don't know if you are going in the right direction or not. So that's the main difference between the off policy and on policy. But then there's a DDPG method. There's also some problem with these DDPG methods is that there's an overestimation of the Q values. So let's say there's so much of coming in the critic network, right? State and actions and a really complex system, and eventually it's giving just one overall optimized Q value or one single policy, which is not feasible, and then there's a chance that there's a possibility of happening the overestimation. So what we do, we use this another method called the TD3, which is a twin delayed deep deterministic policy gradient method. And how we are improving the behavior is using three main things. One is instead of using one critic pair, we'll be using two critic network. And then we will provide some kind of a delayed updates. And then the third is actor noise regularization. So what these three things are, if I try to explain in also like a simple words. So when I'm saying using a two pair of critic networks, so we have these two networks, and then they are here. You can see there's a critic 1 and critic 2. So what it's doing, it's keep comparing with each other and then try to find the one possible, instead of like only one whole network is handling all these states and actions together. But then here we have the true critic network, and then you'll get the better, not the overestimated value, but then the proper Q values. It's let's say if you and your friend is working something together and then you are competing with each other, then eventually the outcome would be something you doing something alone, and but then the comparison give you the better results. So that's the one thing. Second is the delayed updates. So delayed updates is if again, then let's say another example for the delayed updates could be you have some deadline, but then one deadline for you have for your exam, you have your conference presentation, you have some kind of assignments is going on, and then all they have the same deadlines. Then it's what? Then you will not be able to perform perfectly or extra nicely in that for that deadline. But then if you provide three different deadlines for three different tasks, then you can be, or you extend the period for a little bit more, and then you can perform better. So this is like a same, that you are going through all these process, but then you're providing a positive delay, acceptable delays, not like a really long delay so that your network or actor is losing the information of the states. And then the third is the noise regularization, is something that you are providing a positive noise to your system. So when I say the positive noise means, let's say if you're walking on a road and then there's so much of noise and honking, and then someone is talking, crying, so much of drama is going on, so much of noise. And then how can you say like, oh, what is the positive noise? They say a positive noise is like, oh, let's wear some kind of headphone. And it's still some kind of sound you're listening, but then it is something you like it, right? So this is something we call like a positive noise or like a white. So we use the Gaussian white noise for it, and then we provide like some kind of very small amount so that it will differentiate between these two, and then it's not actually affect the overall state of the system. So this is something what is what the twin delay deep deterministic policy gradient method does. So I have implemented this on the different let's say systems, but then for mainly I have implemented it on the drones. So I'll talk about it how I have implemented, but then quickly I will give what are the different kinds of drones are here. So we have a single rotor drones, we have a multi-rotor drones, we have a fixed wing drones, and then single rotor can be the example. You can see the helicopter, multi-rotor could be your drone itself that's used for cinematography or surveillance and all. And then the fixed wing is something like a plane. So the single rotor is like really doesn't take time to vertical takeoff, and then stability is good. But then this fixed wing is like needs a runway to fly high, and then but then they can stay or go achieve a very good height. So that's these are different kinds of applications. So how I have implemented on the drones instead of helicopter or any kind of a plane example. So what I have done, I have used this PX4 controller, which is generally used for the flight control applications. So it's a open source flight control software stack, which is used in many different not necessarily only aerial vehicles, but in other vehicles also. And it provides the autopilot and the control algorithms needed to stable and to make the or provide the autonomy to these vehicles. And we have inside of it, you have an inner loop control, you have an outer loop control. Inner loop control talks about the roll, pitch, and yaws, and then just maintaining the attitude, while the outer loop control will talk about the or use the PID controller, and then that measure the frequency, position, and velocity. So this is a general framework for the PX4. But other than PX4, I've used this Gazebo simulator. So what we are doing, we have a simulator, we are calling our drone to the simulator, and then we have this PX4, which is interacting or integrated with my drone. And then using the ROS messages and services, we are transferring or sending the states to the RL algorithm through the OpenAI gem environment, which is also a framework for the reinforcement learning. And then there you can find multiple algorithms already there, and then you just need to train it and update it according to your environment. So here we do the training, validation, and testing. And then I've used this TD3, where you have two different kinds of network. You have a target network, you have a critic network. So critic 1 and critic 2. The critic 1 is like your network 1, and critic 2, you can call it a target network. And then they keep comparing with each other. And then the new states and updates, based on the whatever the based on how the comparison between both the critic networks is going on. And then you get the max Q values, which should be coming from your target Q values. And this is how I've implemented it. And then here is the comparison. You can see here, like with the TDPG, it's taking time to move. And then with the TD3, it's performing a bit faster, and then less noise in the system as well, and able to eliminate the noise from the system, let's say. And here we have the results from this. So how the reward is converging in the case of TDPZ, and how the reward is converging in the case of TD3. So you can see in the TDPG, it's taking almost 400 episodes. And the episodes is something, let's say, how many steps you are having per episode. If I have one episode, then it means that and it's up to me how I am defining it. So if I want to say, like, okay, per episode you have 1,000 steps, and then you will have like a 10,000 episode, then the number of time steps will increase. So how, with respect to episode, how the reward is converting, how long it is taking. So for GDPG, it took like almost 400 or something, but then like for the conversions, it would taking for the DDPG starting from 200 and then eventually converging to 800, while for the TD3 starting from 200 and then almost converging from 400. So you can see it's like where the DDPG is starting, the TD3 is already converging. And then you can see the learning rate also. And it's better for the TD3. And here's the trajectory travel for the DDPC and TD3. It's because it's overlapping too much in the same coordinates, then it looks like it's not visible or like a proper. But then when it actually you see the drone flying, then you can see like a really big difference how the trajectory is traveled. So for the DDPG and TD3, there are some results for the roll, pitch, and yaw angles, and I'll not go into the detail for that. And then the next thing that I'm working is on the application to manipulators. So here in STO, I'm working mostly with the manipulators. So there are like a different kinds of manipulators based on the number of joins and the links you have, number of degree of freedom you have. There's the articulated manipulators where you are just have a prismatic joints. Then you have a selective compliance assembly robotic arm where you have a high horizontal motion needed. And then you have a Cartesian manipulator where you don't care about this horizontal motion or revolute motion. Like revolute is giving the any angle, and then the prismatic giving only the horizontal motion. So Cartesian is like you don't care about how you are going how you are going horizontal or vertically, but then it's more about how you are moving in XYZ. And then we have the delta manipulator also. So there's a main challenge with these manipulators is about how can you get the precise motion control. So when you are dealing with the joint space, means when you have, let's say, 7-link arm, and then you have 7 joint angles. Now, when you're dealing with the joint angles, then it's easy because then you have to just control angles. But then when you come to the your operational space change, when you come to the task space, which is more about the XYZ, and then you don't care about the angles or at all, but then you more see like how the object or your TCP pose are changing in the XYZ or task domain, then it becomes very challenging. So, and especially this is already one challenging part, and then secondly, when you have a system that has the unmodeled nonlinearities, then it becomes even more difficult. So, and so to provide the solutions to those problems, I have used this ET2 quantum fuzzy neural network, where you have dynamic equations of the robot. So you have a mass inertia matrix, you have a Coriolis system, you have a gravity matrix, and then you have to calculate how much torque is applied to your joints. Or so for that, I have used this, as I said, the evolving type 2 quantum fuzzy neural networks. So in this evolving type 2 quantum fuzzy neural network, I have the fuzzy network and fuzzy system and fuzzy controller, let's say, and then I also have a neural network. So what the fuzzy control system is doing, it's we are not providing any kind of rules. We are not providing any kind of membership functions. What kind of membership? It's like a basic trapezoidal membership functions, but then it evolves. That's the beauty of this controller. So what it does, like initially, I'm just saying, okay, you have a trapezoidal membership functions, but then the rules is not provided to you. So it provides the empty rule base to your network. And then the moment how the changes is coming, how the state is changing, how the positions that coming from the operational space of the TCP pose, and then based on that, it's keep updating. It keeps changing, and then that's how the rules grow, and then it find the correct membership functions automatically, and then also the correct rules for the updating or handling the uncertainties in the system. So here I've used this sliding mode controller, ET2QFNN, and the comparison of the PD controller, and you can see like how the signals change. So when you have let's say the sensor data, when you have a 550 dB of noise, then it's okay. It all seems okay. The moment you increase the noise, how bad it's becoming. But then after applying these ET2QFNN, I have compared that this performs best over the PD controller or the ISMC controller. Other than that, recently I'm also working with this dexterous hand. So this dexterous hand is basically you have again different kinds of hands. We have tendon driven hands, we have adaptive gripper hands, whereas like the shape and when you have a different kind of object, then it's adapt automatically. And then we have an anthropometric hand also, and the soft robotic hands. So these are the different kinds of hands. And then what I did recently, I tried to involve physics into the modeling of this mechanical system. So if I talk about the one single finger, so let's say this thing, what is shown here is nothing but the mass spring damper system, because how many joints I have? I have 1, 2, 3. We have 3 joints, right? And then what we are doing at the every joint, and then this is working as a mass spring damper system. So if I am able to model this thing, then I'm able to model the one joint. If I am model to this thing, second proximal fixture joint, then I'm able to model this thing. And then when I combine all these together, then it becomes behave like a robotic finger. So this first I did some kind of a modeling using the mass spring damper systems. You have an actuator, you have this tendon. So tendon is something like a kind of a thread that is connected with all the actuators, and then try and controlling it. So if you, let's say, pulling the thread, then it's like all the motors are in the connection with each other, and then changing accordingly. So we have a MCP joint, we have a proximal joint, we have a distal joint, and then the change in the actuator, and through the pulley, the overall fingers you can control. So what I'm doing here in these days, I'm trying to involve the physics also in this model. So earlier, instead of using the Euler-Lagrange, I've used this Hamiltonian functions, and I'm using the energy also in the network. So what I'm doing, like instead of just having the position or velocity data, how it's moving, or the angle data, I'm also adding the energy, which is some kind of kinetic and potential energy to my Hamiltonian functions, and then I'm checking with respect to time how much energy is conserving between one joints to another joints, and how they are interacting with each other also. So there's this loss function. With the help of this loss function, we are able to calculate the energy loss when they are interacting with each other, or even just interacting with the while grabbing some kind of a object also. So yeah, this is my current work, and yeah, that's it for now. So today, I mean, what I did talk about, I talked about the different kind of robotic system, balancing systems, helicopter system, drone system, manipulators, and then also as the dexterous hand. So as I mentioned that I have talked with these, I have worked with these different robotic systems, and I have designed different controls for these systems. And I have worked with the reinforcement learning. I have worked with the different kind of like optimal control methods. So yeah, and then in future, I think I'll be more working with integrating this physics informed neural network for not just only just such a small example that is corresponding to the mass spring temper system, but then also like an actual robot. That is something I'm planning to work in future, and let's see how it goes. Thank you from my side.
Thank you, ma'am. We are truly enriched by your perspectives. Next, I move ahead to introduce our third keynote speaker, Dr. Muhammad Ali Khan. Dr. Khan is an assistant professor at the Center for Industrial Electronics, University of Southern Denmark. A senior IEEE member and active researcher, his expertise lies in industrial electronics, smart power conversion, and predictive maintenance for next generation energy systems. I now request Dr. Khan to enlighten us with the keynote address on renewables reimagined with intelligence. Please.
Hello, am I audible right now?
Yes, sir, clearly.
Yeah.
Hello, excuse me.
Yes.
Organizer, I think I just arrived because I just finished my Friday prayer. Bit late, I think maybe 5 minutes late. So when is my turn? Hello.
Hello,
can
is
you
there
hear me?
anyone from the organizing team here that can help, Professor?
Can you hear me?
We can hear you, but I don't know if there is anyone from the organizing team who is there right now.
Yeah. I'm supposed to deliver, I think, 2 p.m. Malaysian time. Maybe because here is Friday, I just finished the Friday prayer, so I was rushing from the mosque to my room. So that's why I think I was delayed by 5 minutes. Any organizer here?
I don't know if, yeah.
So could you
Anyone
please
from-
repeat your concern? We're here.
Mr. Gupta.
Yes, sir, Sathar.
Yeah. So how is my turn? My name is Ishak. Ishak Aris from Malaysia. Can you contact your
I think
chief?
there's some misunderstanding in the order. You have to speak first, if I'm right, sir?
Yes.
All right, sir. Please excuse us for the same. I'll just start again. Just a minute, please.
Can you, Dr. Muhammad, sorry, yeah.
No problem, no problem.
Because I was here is like around 2 p.m. We pray Friday prayer
Yeah.
around 1:10, something like that.
Yeah, it's okay. I think it's overextending already, so that's not a problem.
Where are you from? Yeah, from Denmark, yeah?
Yes, I'm working in Denmark, sir.
Okay, okay, good. Which area?
My area of research is completely using AI for power electronics and power
Oh,
system.
AI for power electronic, AI. Okay, okay. My area also in power electronics.
Okay. I think I'll proceed with my address then because it's taking time anyhow.
Mr. Gupta, how are you going to arrange, Mr. Gupta?
I don't know, like no one is clarifying it
So
properly.
there's some problem with the audio. Could you please switch to chat for just 5 minutes?
Hello, I'm audible.
Yes,
Yes.
Mr.
Yeah, I'm the faculty coordinator for this session. Actually, Ishaq sir, it's your turn officially because the timing is allotted to you. But because we are running out of time, because our first session is too delayed, so we are giving opportunity to talk to Ali Khan sir first, and then we'll continue with you, sir.
Okay, so Dr.
If you
Muhammad,
don't mind. Yeah.
yeah, Dr. Muhammad will talk first, and after that me.
Dr. Muhammad Ali Khan, you can start your session, please.
Okay, yeah.
Ishaq sir, please wait after this session. We'll continue with you.
Okay, okay, all right, okay, no problem.
Thank you, sir.
Thank you for the clarification. Yes. Hi, everyone. I'm going to talk about renewable, reimagining it with intelligence. So we have been talking too much with intelligence, AI and AI ML and all those things going around. And I would like to just concise that and see how we can do this when we are talking this whole of different kind of things with when we are talking power electronics now, because a lot of power systems nowadays are using AI and ML and all these applications going forward. So just to start, I'll give a brief about myself. I am Mohammad Ali Khan. I'm working as an assistant professor here, and my expertise is AI in power applications. I have been a part of Amity University during my master thesis, and after that, I have a work experience. I have been working in Denmark. Before this, I was working in Czech Republic as well, and my research areas are mostly using AI for different applications, from digital twin till multiphysics modeling and all that scenarios going around it. Just a brief about where I come from. Dr. Singh, before me, just told about SDU University. So she was based in the main campus. I am based in the Sonneborg campus. We are very much closer to the German border. And at the German border, the good opportunities is that we have a lot of companies around by with power systems and power electronics. So we have Siemens and Danfoss right around the corner over here. And in our particular department, I'm working in Center of Industrial Electronics. We have multiple different portfolios. We work with passive components. We work with energy drives. We work with control and production of smart grids. So we are doing research in all different aspects and scenarios going through it. So you can have a look into that if you are interested. The group I'm currently working with is Control and Production in Smart Grid. We are working on multiple projects and multiple scenarios when we talk about power management, power scaling, cable managements, and integration of hardware VHRs to hydrogen energies and all this kind of aspects of things. So it gives us a very great overview of things, and we have a very active lab over here. We are a growing group right now. We don't have a lot of researchers right now in this particular center. We have the total center has a 52 researchers group, and my group currently here we have 4 people. But yes, this is how we are starting right now. Let's come to the topic for the today. Today we are I'll be going through talking about a brief about the introduction, then how the evaluation of AI in power electronics has taken place, then some of the need of the AI. This kind of cases study is what I have been doing. I'll be just not taking too much of your time. I'll just give a brief of each of the areas which we have been moving forward and what are the future concerns when we talk about AI in power electronics. So first, why do we need AI for power engineering? We have been using AI as a key term right now, and everyone has been using it too much. But why do we need it? Specifically when I talk about power engineering, what difference does AI bring to the table for power engineers? So there are some challenges with power engineering. There are challenges of there is a lot of complexity coming in when we have now renewable energies pumping into the grid, and the scenario has started looking very big and very denser with multiple power systems into the picture. We have EVs now. We talk about EV to grid, grid to EV. This kind of scenarios, which is also making the power system more complex as we go forward, and obviously the efficiency and reliability of the power system has been always very tricky. What will AI bring to the table when we do all this power management and power scaling? We generate a lot of data, and we need by using AI, we can use this data in a very good manner of doing the whole management in much more optimal sense. We have better prediction, better we can avoid some faults when we are doing good prediction analysis and all that sort of aspects. We also enable a lot of adaptability. So our control systems based on different kind of scenarios or different kind of faults or fallbacks, we can adjust our control system scenarios. And at the end, we have impacts. So it impacts the uh, energy management schemes. It impacts the power quality of the system. It also makes system more smarter and resilient. So this is one of a very basic research which was done a few years back by one of colleague from Aalborg University, Huai Wang, and his group. So they were doing is that they have different scaling and techniques which are used for AI, and they are seeing how they can be used for different configurations, like maybe for design, control, maintenance, and how are they flowing through the different scenarios, like are they going into optimization field, are they going into categorization field, are they going into regression field. So the opinion with this is that AI is not just an option, it's an essential feature which we need into power electronics to make this data and system more reliable going forward. How do we evolve? How does the evolution in AI takes place for power electronics? So at the very early stage, it was just a technique we were using for power optimization. Then moving forward, once we felt we have good amount of data and control over it, we started using machine learning for power electronic controls. But we are never satisfied. So we move forward, and then we found out that, okay, we can do something with predictive maintenance, we can do something with lifetime monitoring and fault diagnostics and all those aspects as well. Further closer right now, we can see now we have deep learning aspects to the system. So previously we had just some faults we know about, but there are certain faults which are not categorized properly. So those categories, how they will be created, and uncategorized faults can be taken to care of. So those things are done by deep learning and the aspects with it. And the other thing is also we have now the EV came in the picture, and then we have topics such as energy harvesting. So because we already had a data generated and we had a good idea of how things are working, we used that kind of data for harvesting, power modeling, and all those parts. The last right now, which what we are doing is that we are building towards AI for much more improve converter modeling improvements. We are using it for renewable integrations, and we are moving in that direction as the days surpass now. When I talk about need of AI in power electronic application particularly, we are generally using it for multiple scales of things. First is energy efficient optimization. So we want to optimize the energy so that the power distribution is all over the spectrum, not just very particular places. And how we optimize it, that's another story, because we have multiple storages coming into the picture, energy storage, energy schemes. So all that we need to take into consideration. Then we have fault detection and diagnostics. We talk about a lot of AI-based faults, and this faults, by using AI, we are able to figure out what are the faults that are taking place, and we try to clear that fault as soon as possible. Predictive maintenance is also gaining more traction nowadays, because now when we are able to identify faults, we can know how the system is getting degraded, and we can maybe plan for a failure beforehand. The other thing is smart grid management. So in the smart grid management, what we are doing is that we have multiple sources, and we are trying to manage at which instance are we going to use renewables, and we want to reduce the grid consumptions. So we are trying to manage the renewables in such a way that grid can be only used as a sink. So it's acting as a big form of a battery, and we are trying to make maximum utilization of the renewables to the consumers. Same way we have load management. We can have multiple cyclings of load. We know that in summer months we don't have any more heating loads, and in the winter months we have high heating loads. So in summer months we have air condition in Indian case scenarios. So that fashion we try to figure out what kind of load are we going to utilize, and uh, as I say, if an air conditioner is operating, our reactive power dynamics will change very different from that of a heating load. So that way we can make a good power spectrum of things, and we can make sure that the power is satisfied at all the times. Then we also want to make a grid, sure that the grid is stable. Obviously, when we have active and reactive power into consideration with our things, we need to make sure that we are not making a grid go very weak or distable, because also we are pumping in a lot of renewable energies into the picture. So we need to make sure the grid is not going off bounds at times. Control optimization, when we talk about individual converter, nowadays a lot of fluctuations are there and now this individual converter can use AI for good control strategies. so that the efficiency of the converter is better, the lifetime of the power switches are better, and that aspects. We use it for energy harvesting now. Nowadays, this is a very nuanced kind of a thing. They are using carbon capture and generating energy from the carbon that has been captured in the atmosphere and moving in that direction, which is a long way to go, but the process has already started with this. And the last is energy management in a building. This is very similar to all the topics which I have been talking. We are trying to make an energy efficient building. So we are making sure that the building is much more energy dense. It's much more better. It's we say green energy buildings. So the heat which is generated from different aspects from refrigerators and are captured in and they are used for the heating purposes. They are trying to make this kind of a recycling environment with AI, not just power electronics, but also in general. This energy management in building is not just focused on one application of power electronics. Talking about some of the case scenarios, so I have been working in this field extensively for now 7 years, I guess, and I have been using AI for different purposes. The first purpose which I have been using it for was forecasting patterns. So let's say I have decided this particular lush green patch of land is where I will be setting up a new building. When you are doing you are starting a planning stage, you always make a predictive assumptions. You make need to know how much this will increase my load, how much if I put a panel out on the top, how much will it generate, and all that kind of aspects we need to take care of. So here I'm not doing that long term, but I'm doing a very short term prediction. What I'm doing is that I have uh, uh, we were working on a project where we had hydrogen and battery management systems so how much are we using for electrolyzers and how much are we using for batteries, and based on that management scales, we did 1 day ahead prediction of how much power generation is going to take place from solar, wind, how are we going to reduce the grid into the picture, and how the load profiles are going to look. So when you have extensive data of patterns, it's always good to extrapolate those patterns and make a predictive analogy for 1 more day or 2 more days. This can be done for a very long term also. That this can be done from a small term also. Depends on how much of a data you have and what is the resolution of the data you are using with. So this was one of the interesting works which we did. We also did something with the cost analysis here. I didn't add that. So as an engineer, we are very concerned always about how much power and energy we are playing around with. But when you go and talk to the companies, they are more interested on how much money they are going to make. So that kind of cost estimation is always very informative for them. The second thing which I did particularly for power electronics part here right now is that we started using AI for converter modeling. So right now in market, you see a lot of a lot of devices. You see silicon carbide, GaN as a semiconductor switches. Then we have in capacitors, you have a lot of options. You have in inductors, you have a lot of different types of cores. You have different type of windings. So this lot of options also create a problem that we don't know which is the best component for our particular requirement. So if I'm designing a converter, in this example, I'm just designing a boost converter. But if I'm designing a boost converter, let's say for renewable application, it's totally different than a converter that is designed for a EV charging. For EV charging, you need a high current converter. For renewable energy application, you need high voltage converters. So when we have this kind of scenarios with it, uh, again, what we try to do is that the first half of the study, like this part of the study, we are just doing the basic mathematical modeling. Uh, Nowadays, that is called multiphysics modeling. So we are doing a multiphysics modeling of a converter. We have break down the whole mathematics of a converter and try to figure out what are the variables that we take into considerations. Once we have identified all the different variables that are to be taken into consideration, and we know okay, these are the particular variables that will impact the selection process for us. Then we come and design an optimized device selection framework where we are just using the efficiency as one of the data. So first, when we do the modeling, we are generating a lot of data, and then I'm using those data for using for AI part. So we have taken efficiency as one of the data. We have taken volume, the size of the converter as one of the data. We have considered uh, total losses, I think the thermal resistance as other two sets of data. And based on that, I've used certain part of the data for training and certain part of the data for testing. And then we run machine learning algorithms to just tell us that for this particular application, this kind of switch, like maybe silicon carbide switch is better if you're using it for a high voltage application. But if you're going for a high power density GaN is the best solution. So that kind of learning is taking place. Right now, the curves are looking very different because obviously I didn't have a good amount of data to train my system. I just use one silicon carbide and one GaN data. But the idea was to create this framework and deliver it to a company, and then now they can make the database for that and test for their different applications. So this was one of the ideas which we are using for designing a power converter. Controlling of a power converter, this is one of the tasks which I did during my PhD back when I was working in Jamia Millia Islamia. So here what we are doing is that when we talk about a converter control, we have multi-stages of it. We have uh, there is a inner loop control where we have the voltage and the current control, but there is an external controller nowadays which we are using for because the grid is getting much more intensified nowadays. So we are trying to make sure that we are not overburdening the grid. So here we are using identity detection, fault right through, and fault tolerant control. And all these three stages we are using with AI. So for identity detection, what it means is that when my grid encounters any kind of a failure, my converter should be capable enough to disconnect from the grid and feed the local loads. That is the whole idea. And when the grid comes back online, I need to reconnect back to the grid. So the first part of that is that in islanding detection, what we are doing is that we are trying to figure out when the fault is taking place. Whenever the fault takes place, we disconnect from the grid and we operate alone as a single unit, supplying a single load. At that same time, when this kind of disconnection takes place, we have got certain grid codes that say, not certain, I mean, the most of the grid codes say that we need to make sure that the converter is also supplying, trying to support the system. So we cannot directly, okay, we found a fault, let's disconnect. We cannot do that. We need to make sure that we are trying to stabilize the grid in the first hit. So for that, fault right through comes into the picture where we are injecting the reactive power to make the system go try to recover. We are trying to inject reactive power to make sure that the voltage level is balanced back. But at certain time, that is not a possibilities. Then we have the last one where we are like, when this kind of disconnections take place, we make sure that the uh, from islanded mode to grid connected mode and grid connected mode to islanded mode, there is no transients when this whole process is going through. So this is also one of the interesting studies we did. Then this is a work of one of my colleagues, Satya Bharat. He has been also a part of Amity with me. At the same time, we were sharing the same batch. So he has been working with fault diagnostics. So all the different type of faults, each fault has a signal, signal analysis. They have different type of signal studies and structures, and based on that, he was doing the fault diagnostics. You can have a look into this paper and maybe reach out to him. It will be really nice for him. One of the recent things which we have been starting to doing is that we are modeling devices nowadays, because when we talk about loads, the loads are not very linear sometimes. So I was working with electrolyzers recently, and electrolyzer is not a linear load. It's not a non-linear load. It's a electrochemical load. So for electrochemical load, we don't know how the dynamics is going to look like. So in multiphysics modeling is what we do is that the different aspects, the electrical aspect, the thermal and the physical aspects, pressure-based aspects of the whole model is break down into mathematics. And then we try to see how they intertwine with each other to design algorithms. this is not a lot of AI, it is more of mathematics towards it, but it makes a very good sense when we are applying it, because I don't want to use a lot of data anymore, because companies are not very happy to give you a lot of data. So these are one of the replacements when we talk about how AI is moving in the other direction nowadays. So this is one of the areas which can be taken into care. Cybersecurity is also one of the research areas which nowadays, after what has occurred in the European context, a lot of universities have put their focus towards cybersecurity. So what we do here is that we try to inject the fault first, try to become an attacker, try to figure out, okay, what happens when I inject a particular fault. I make a system think that there is a fault, and then when an actual fault occurs, how those patterns are not overlapping over each other. We try to figure that out. I have used physics informed spline learning long back on this whole scenarios, and we had some very interesting results. Obviously, I'm putting the links to all the articles. We are running short on time, so you can maybe have a look into this ideas with AI. And if you feel like, you can reach out to me, not a problem. This is where the future is moving towards with AI. So we are moving towards a lot of things with digital twin. So in digital twin, what we are trying to do is that we have a physical platform, we have a smart grid, let's say, or multiple converters connected into a series of loops. And now we want to make a digital inference of the whole system, so that before the fault occurs or before some uneventful condition occurs, we can do that kind of uneventful conditions and see how our system will respond to it. And if we need to take some critical actions, we have pre-planned for those critical actions. That is the whole idea with this digital twin. Now, the major concern with this digital twin is that we cannot do it with data, because so much of data, so much of processing will take a lot of energy. The better way of doing it is using multiphysics applications, where you do the modeling based on mathematics, so you're not depending on data anymore.
Sorry to disturb you, sir.
Yes.
Sir, now from now onwards, I am the student coordinator once. Sir, with due respect, I just want to say you that, sir, actually we have a much limited time because our next session is going to begin soon.
Okay.
So we are also waiting with sir, next speaker. So if it's possible, sir, please can you wrap it up a little fast?
Yeah, just I have one more slide. That's it.
Yeah, thank you so much, sir. Thank you so
No
much.
problem. No problem. So this is what with the digital twin part. I'll just go to the last slide, because this is actually much more important for me right now. Concerns with respect to using of AI. This is very critical area, and we have started working on this. So if I have to save a patient, I don't stab him multiple times. So using AI right now is for saying I'm using AI for energy management, or to protect some energy or make energy renewable resources, is like you are stabbing a patient, saying that, okay, I'll clean your wound soon. Because whenever you are using a lot of AI or data generation, or even right now you are using chat GPTs and all, it goes to a server, and that server consume a lot of energy. So I cannot save energy by consuming energy. So this is one of the major concerns which we have to see, and moving forward we have to look into that. How much AI do you need, and how much you don't need? And you need to be very mindful of those things. So this is one of the analysis which we have done recently, and yeah, you can have a look into this. Thanks for listening. That was all from my side.
Thank you so much, sir. That was
problem.
indeed an inspiring talk. Thank you very much, sir. Finally, it gives me great pleasure to introduce our fourth keynote speaker, Dr. Ishaq B. Aris, sir, joining us from Malaysia. Dr. Ishaq bin Aris, sir, is a professor at University Putra, Malaysia, with over 2 decades of academic and research experience. He specializes in power electronics, renewable energy integration, and distributed generation systems, and has authored numerous impactful publications in those areas. I now request Dr. Aris, sir, to share his invaluable insights with all of us present here on the title Current Trends and Future Prospect. Now I have also Pyare Mohan Tiwari, sir.
Hello. Dr. Ali, thank you for giving a very informative talk. And I would like to welcome Professor Isaac.
Yeah.
And yes, how are you, Professor Isaac and Dr. Ali? I hope
Yes,
you
yes.
all are good, right?
Good. How are you?
All fine, yes.
Nice to meet you
And
again.
we were hoping you both to be in India for this conference, but yes, I understand traveling and sparing time is very difficult. So that's why this online is a good mode where we can connect and greet each other and listen to each other. So thank you, Dr. Ali, and welcome, Professor Izzad, for
Okay.
this conference, right? Thank you.
All right. Thank you.
Yeah, Ishak sir, now you can start your presentation.
Okay. Let me share my screen. Okay. First of all, I'd like to say thank you very much for inviting me to take part in this conference. My title of presentation is Current Trends and Future Prospect of Multi-Mode Electric Vehicle Communication System. First of all, I'd like to say I'm very sorry because a bit late, about 5 minutes late, because due to my colleague praying time, here in Malaysia, a Friday prayer. So I managed to quickly after the prayer quickly come back to my office. So they managed to join all of you. So hopefully that the knowledge that which I'm going to share can be beneficial for everybody. Okay, so communication system for now, if you look at EV is the main thing in the in the transportation. So previously we have what I call it internal combustion engine. Now replaced by the EV, also another one of application of the power electronics. So a lot of power electronic stuff is used in the EV. So, but I look into the angle of a communication system. Right. So this is my University Putra Malaysia. It is in the capital city of Malaysia, Kuala Lumpur. So if the university is, if you're coming at the international airport, it's only about 40 minutes from the international airport, Kuala Lumpur. So if you are around Kuala Lumpur, then you can contact me. So then we can see each other. Right. So this is my presentation. First, I'm going to give the introduction, then talk about this previous vehicle communication system, current vehicle communication system, and future vehicle communication system, then conclusion. Okay. So this is what I call it, what we have for, let me, okay. This is what we have for roadmap. I would say it's a roadmap for the transportation system. If you could see that this is until 2050. Okay. So so normally we forecast so that what type of vehicle that going to be around in the next maybe 10 or 20 years to come, so that we can look into the readiness of this type of vehicle. So currently we have the ICE, internal combustion engine. Then now the hybrid is introduced back few years ago. Then followed by what I call it, this PHEV, then followed by BEV, battery electric vehicle. Then this FCV is the fuel cell. based or hydrogen based vehicle. So this is the thing. There is like a short term, medium term, and long term planning for this type of vehicle. So normally this type of vehicle, they are not moving out suddenly. So that is in phases that they introduce it slowly, so that the customer can take the advantage of the technology. Yeah? So this is some of the forecasts of all this type of vehicle. So if you can see that currently in until 2050, so currently if you look at there is what I call it introduction of the EV into the market, yeah, because internal combustion engine give a lot of pollution. So and for the EV, less pollution, yeah, maybe concentrated pollution, even though the vehicle don't have any pollution, zero emission. But when you charge the car, so you need the power from the power station, and the power station emit do this emission as well. Yeah, but at least it's in control manners. Yeah? It's in control manners. So then for type of vehicle, so normally we have like the concept of intelligent energy efficient vehicle. So normally intelligent energy efficient vehicle normally consists of these all four. Yeah, this ICE, BEV, this hydrogen HFCV, and also HEV. So all of this is known as what I call it intelligent energy efficient vehicle. So normally we look into this. Yeah. Okay. Then this is the what I call it the type, the differences between the ICE and also the EV. So normally the ICE, you have of course the fuel tank, then followed by the internal combustion engine. Yeah. Then based on this fuel tank, the fuel is burned. Then the fuel will be converted into pressure. Then the pressure will move the piston and move the wheel. And then after that, the car is moving lah. For EV, so normally we don't use any fuel. Normally the BEV battery, they use the power source is from the battery packs. So this is the main power source will be used to run the motor. Yeah. So through these converters. Yeah. Converters. So normally they have these DC to DC converters, DC to AC inverters. Yeah. Then go into the motor. Then moving forward. Then also, of course, they have also regenerative braking. Yeah. Regenerative braking normally. There is a certain angle that the car is producing energy, yeah, because the machine or the electrical machine used in the car, it can function both as a motor and also generator. One particular time it can behave as a motor, the other one it can behave as a generator. So in that process, they use a lot of these power electronic converters. Yeah, so that is the things. So and for the internal combustion, this is I'm not going to elaborate this. So this is the structure of internal combustion. What you have like all these the flywheel, the combustion chambers, all the piston. Yeah. So when the fuel is burned into this combustion chambers, then it turn into I call it the pressure. Then the pressure push the piston down and move the wheel and link it to the transmission and so on. Yeah, so this is the things. So we have projects for the internal combustion. Luckily, I was involved with this the project from our car manufacturer, Proton, under this what I call it internal combustion, and also we also have project with EV. With our Prodwa, one of our local car producer, to design their EV system. Yeah. So this is internal combustion. This is how it started. So this is the research project. The fuel is a neutral gas, complete neutral gas, CNGDI, compressed natural gas vehicle. So this is the engine. So the engine need to be calibrated. I call it fully before it can be put into the car platform. Yeah. So that just quickly we go into this one. Yeah. So this is how it looks. So then you calibrate the ECU and so on. So during this time, we communication normally we use CAN bus for the vehicle. Control area network. Yeah, so that is the communication system we use. There is a CAN high and CAN low. Yeah. So, and this is inside the control room. When you calibrate the ECU, the controller to run the vehicle. Okay. Okay. I should quick just short video. And after we calibrated the vehicle, then you put the vehicle into the vehicle platform. Yeah. So then this is SOD. This is internal combustion. So during this one, we use communication CAN communication system. Sorry. Then this is what I call it. Okay. Then the car is now moving tested from. So this is 100% developed by us for the Proton car manufacturer. Yeah, from the engine room. Then when we design the engine complete, all the controllers, engine, and communication system is developed by us. This is direct injection engine. Yeah, 14:1. Then what I call it, the structure for the hydrogen car. So normally it based on what I call it. It based on what I call it EV as well. Yeah, but the fuel cell which produce electricity, normally you need the fuel cell combined with the oxygen, then the hydrogen, then it will generate the electricity. So the powertrain is still electric vehicle. Yeah, only the source of energy is different compared to the battery. So that is the difference. So in terms of this is the structure for the hybrid combination of internal combustion, and also this is the internal combustion and also electric powertrain. Yeah, so it's combined. So there is like what I call it, series hybrid, parallel hybrid. So it's depend on the what you need. Yeah, so we need to go faster. This is a series what I call it, hybrid, and this is a parallel hybrid combination. Then this is a mixed configuration. Yeah. Okay, so now we go into the previous currently what I call it, the one you saw in the CNGDI vehicle. We use a CAN. Yeah, so CAN we have CAN high and CAN low. The problem is this thing is they are very limited. The bandwidth is small, so you cannot.
Ishaq sir,
Yeah.
so sorry to disturb you, sir. Sir, actually, at 12:45 we have our next session. So today, so sorry because today there was a delay and all. So sir, if you can wrap it up a little fast, it will be very good for us, sir.
Okay. All right.
So sorry, sir, for the inconvenience. But thank you so much, sir, for understanding us. Thank you so much.
All right. Okay. So this is the vehicle current system. So this is what we propose. Yeah, vehicle which we can multi-mode. Multi-mode mean that type of communication is like a wireless, CAN, and pass optics all together. We combine together. So then this is the CAN protocol. Yeah, and this is the application. Some of the car manufacturer use it, and this is our system for our vehicle communication system. Then this is another configuration. This is the devices that we are using. Yeah. Then this is the structure for the multi-mode. Yeah, multi-mode design. which you combine all the application, and this is the things that we are using. Yeah, Xilinx chip to have this multiple mode of ni based on this processor. And then this is some of the things that we have designed, tested based on that one. So all this multi-mode. Okay. So since the time is not much, and I just keep the thing. And this is some of the commission that we have done. Then this is the IP display. Then this is some of the application which link to the wireless system, a database cloud as well. So the cloud can be linked to this thing. Yeah. Then this is some of the application. Okay. And I think I skipped. This is the structure for the EV and all the design. So from the I call it battery, then PDU, then the powertrain, and then some other devices into it. So I think I quickly, and then this is the battery pack. We use a lot of this communication need to be there. Then this is the design. This is the structure. Yeah. This is the BMS. Okay, and this is the charging part. Yeah, and onboard charger. Okay, this is the structure for the charging, and IP display design as well. We design for this. Yeah, so using the multiple multi-mode protocol. Yeah. Then this is the platform that we use for the EV from Produa. And then this is the system for the first version prototype that we are using. So you can see all the component there. This is the control panel. This is the powertrain. This is the battery pack. And this is the charging. This is some of the video that we can check. Yeah. And then this is the battery packs. Yeah. Then this is the battery pack. I just show it if you can. Right. This is how we test before we put into the vehicle platform. And this is then the motor is testing. Yeah. Okay. This is what I call it, the control panel. This is how we need the first prototype. Yeah. This is all the control panel. Okay. Okay. So then this is we participate in the auto vehicle Nation Auto Show under Produa. So this is how it done using our multi-mode communication system. Okay, and this is the vehicle, the EV that we are producing based on that one. Okay, I think because the time is not much, otherwise we can spend more. I hope that you can get for the future. Yeah, more will be coming. Yeah, hopefully that with this including this AI, and also we need very strong vehicle communication system, especially on the safety part. Where we could all this avoid all this scamming part type of things. So that we need secured communication system, so that the car cannot be hijacked by some other people. Yeah. So that with that I conclude the presentation. Yeah. Thank you very much.
Thank you so much, sir, for your such valuable insights and for guiding us through emerging dimensions of research. With this, we conclude our plenary session, the exchange of knowledge and vision that we have experienced today is truly invaluable. On the behalf of organizers, I extend my heartfelt gratitude to all our esteemed keynote speakers for their time, efforts, and wisdom. I would like to extend a special thanks to our faculty coordinator, Dr. R.K. Viral sir, for the constant support and guidance. To all the participants and delegates, thank you for being the part of this session with such enthusiasm. Let us carry forward with the ideas sparked here into our research, teaching, and innovations. Thank you, and we now move next ahead to the next segment of the conference as per schedule. Thank you so much, sir. Sir, Amity host, you can end the meeting now.
Yeah. Okay. I want to get some photo. Is it okay? I want to display back the presentation. I
What,
want to
sir?
get some photo, right? Just to capture the screen. Let me open back my presentation. Just I want to open, then I want to take the photo. Did you, because I don't have the photo, yeah? Give me some few
No
minutes.
problem, sir. No problem, sir. No problem.
Give me a few minutes. I just want to just few minutes. Let me this one. Okay. Where is my things? Wait, where's my presentation? I cannot see my screen. Okay. That's the presentation. Okay. Wait. Wait, because I can share the thing. Wait. Just give me a few minutes. Cannot see that. Wait, let me check. Just let me check.
Sir, is the photo clicked?
It's I cannot print. Wait, okay, now. One more. Because I cannot see. Yeah, I thought it's gone just now. Let me check because I need to make sure that. Can you? I cannot name. Where's the screen? Can you hear me? Hello?
Yes, sir. Yes, sir.
But I cannot open up the.
Sir, I'll tell you one thing. Just share the screen. I will take a screenshot and then we'll send it to you.
Okay.
Yeah. Okay, sir. That's fine.
Wait, share the screen. How?
Sir, the last time like you shared the screen, you can share the screen again.
Okay. Join. Okay. This. I got some problem. Wait, just give me some time. Continue. Okay, this the thing. Okay. You okay? I share. Then you take my snapshot. Then yeah. Okay. Let me open up this thing one more time. Eh. Share. Share. Okay. Can you do the snapshot now?
Just a second, sir. Doing it.
Okay. Make sure my photo also there.
Yeah. You are also visible, sir. Just a second. Now you are visible more.
Yeah.
Just a second. Yeah, just a second, sir.
You double check.
Just yes, sir. Double checking it. Just a second. Yeah. Now it is good. Just a second. 3, 2, 1.
Okay. Can you send it to my email?
Yeah, sir. I will just share you. Sir, can you write your email ID here or something that I can share
Okay.
it?
How
In the chat box. In the chat box. Just stop the share screening and just write your email ID in the chat box, and I will
Chat
forward
box.
your.
Okay. Wait. Where is chat box? Here. Okay. All right. Okay, ID. Okay, can you get it? It's _er@upm.edu.my. Okay, that's what it. Can you send it?
Sending it now only, sir. Just check, please. Gmail. Yeah.
Okay, you already sent,
Yes.
Okay, let me check my email.
So please, can you now check your email? Have you got the mail?
Okay. Okay, I receive it. Thank you.
Thank you so much, sir. Thank you so much.
Okay, bye-bye.
Bye bye, sir. Thank you so much. The Amity University host, sir, you can end the meeting now.
Okay, all right, all right.
You can leave the meeting.
Yeah, yes, sir.
Yes, I'm